What if the moon vanished tonight? Instantly, the familiar glow in our sky blinks out, plunging moonlit nights into a darkness over 100 times deeper. The oceans feel it, their powerful tides slackening, and over the very long term, Earth's seasons begin to drift off their steady beat. Let's flip that switch and see what really breaks when our planet's biggest companion goes missing. Stand on that beach at night. One moment, a silvery path glitters on the water. The next, it's gone. A full moon provides about a quarter of a lux of light on the ground, just enough to see by. Lose the moon, and all you have left is starlight. That's just 1 or 2 thousandths of a lux. Your eyes would register a world between 100 and 250 times darker. That's the difference between a dimly lit path and stumbling in the near total blackness. Your eyes would struggle to adapt. Soft shadows vanish. Trails, docks, and the edges of waves all fade into one deep, uniform gray. You would still see bright planets in the Milky Way, and that part would be spectacular. But the easy, reliable nightlight you took for granted is gone forever. Campers and night hikers who once navigated by moonlight would now find their headlamps absolutely essential. But the moon is so much more than a light. It pulls on our oceans with a gravitational grip more than double the strength of the sun's. This constant tugging and stretching creates tidal friction, rubbing on the seafloor and along coastlines. This process burns off an incredible amount of energy as heat. Today, the global tide machine dissipates about 3 to 4 terawatts of power. Remove the moon, and you yank the main handle of this planetary mixing stick right out of the ocean. Look up at the sky. From now on, there will never be another total solar eclipse. Ever. Those rare, magical 2 to 7 minutes of midday darkness, when the sun's corona blazes in the sky, are a thing of the past. No more eclipse chases across continents. The precise orbital dance that created them is over, because one of the dancers has left the floor for good. The monthly rhythm of the sky dies too. No more thin crescent, no first quarter, no full moon. For millennia, humans and animals have used this simple, reliable clock in the sky. It told us when to plant, when to fish, when to hunt. Now, that cosmic metronome is silent. Nights are just dark, and then dark again, without a predictable pattern of light and shadow. There is one upside. With no moonlight to wash it out, every single night becomes a perfect deep sky night for astronomers. But while stargazing wins, science loses a unique natural laboratory. Total solar eclipses gave us our first clear views of the sun's atmosphere, the corona. In 1860, astronomers sketched a huge eruption, a coronal mass ejection, visible only during an eclipse. And in 1919, an eclipse allowed scientists to measure starlight bending around the sun, helping to prove Einstein's theory of general relativity. So what about those tides? They don't vanish completely. The sun still pulls on the oceans, creating its own tide, which is about 46% as strong as the moon's. But here's the thing. Coasts and bays are fussy. Their unique shape can amplify or dampen tides in unpredictable ways. So while a typical tidal range might drop by a factor of 2 or 3, the actual result depends entirely on where you are. Shape is everything. Take the Bay of Fundy in Canada, home of the world's highest tides. Its spring tidal range can top 16 meters, over 50 feet. Because the bay's natural rhythm is perfectly in sync with the moon's tidal wave. Remove the moon, and you break that perfect duet. With only the sun's push, Fundy's tide might shrink to roughly 5 to 7 meters. Still huge by most standards, but no longer the world record monster it once was. All around the world, ports and harbors built around big tidal swings would suddenly feel awkward. A wharf designed for 10 meters of rise and fall might find its lowest ramp ending high and dry. Ferries could miss their docks. And vast mudflats, crucial for migrating birds, would stay exposed for longer, changing the entire coastal ecosystem. The simple act of getting a boat into the water just got a lot more complicated. Tidal power stations would take a catastrophic hit. That's because the energy you can capture is incredibly sensitive to the speed of the water. Power scales with the cube of the current speed. This means if the current slows by half, the available power drops by nearly 90%. With only the weaker solar tide driving the flow, global tidal energy output would collapse by more than 75%. Massive turbines would spin slowly or stop altogether. It's not just about energy. Strong tides act like a giant plunger for our coastlines, mixing fresh water with salt water and flushing out pollutants. Weaker tides mean this flushing action slows way down. Water stagnates. An estuary's residence time, how long water sits there, could stretch by days or even weeks. This dramatically raises the risk of oxygen-starved dead zones, especially in warm weather. Surprisingly, the length of your day wouldn't change overnight. It would still be about 24 hours. But the slow drift in day length would change. Right now, thanks mainly to the Moon's tidal drag, Earth's day is getting longer by about 1.7 milliseconds per century. Without the Moon, that braking force is mostly gone. The lengthening would slow to a crawl, maybe half a millisecond per century. A tiny change for us, but a significant one on a geologic timescale. The familiar rhythm of spring and neap tides would also end. That fortnightly dance, where tides get extra strong when the sun and moon pull together, and extra weak when they pull at right angles, is a product of their combined forces. With no moon, that monthly pattern of fat and lean tides vanishes. The ocean's pulse becomes much flatter, more monotonous. Now let's look at the big clockwork. Earth's spin axis isn't perfectly stable. It wobbles slowly like a spinning top. This is called axial precession, and the full cycle takes about 26,000 years to complete. The Moon's gravity provides most of the torque driving this wobble. Remove it, and the precession slows way down. The period stretches out to roughly 80,000 years. This fundamentally retunes the long-term relationship between Earth's seasons and its orbit around the Sun. But here's the change that really makes climate scientists sit up. Earth's axial tilt, its obliquity, is remarkably stable today. It rocks gently between about 22 and 24.5 degrees over a steady 41,000-year cycle. The Moon's constant gravitational tug acts like a leash, keeping that tilt in a narrow, predictable lane. Without the Moon, that leash is gone. Models show that over millions of years, the tilt could begin to wander chaotically, swinging wildly from less than 10 degrees to more than 45. This long-term instability would mean wildly different climates in the distant future. A high tilt would give the polar regions brutal, ice-melting summers with constant direct sun. A low tilt would flatten the seasons, allowing ice sheets to grow far from the poles. The Moon is the metronome that has kept the beat for Earth's ice ages. Without it, that steady rhythm is replaced by climatic chaos. The deep ocean would also feel the change, but on a slower timeline. A significant chunk of tidal energy creates massive underwater waves that mix the deep ocean. Lose the Moon's share of the tides, and you shave off about half to 3/4 of a terawatt of that deep mixing power. Over centuries to millennia, this would make the abyss more stagnant, slowing the global ocean conveyor belt that circulates heat and nutrients around the planet. On land, animals that hunt by the Moon's clock would have to adapt fast. In Tanzania, for instance, studies show that lion attacks on humans peak during the darkest nights, the week after a new moon. Take away lunar phases, and that monthly spike of extreme darkness is gone. Instead, every night is simply dark. The cat and mouse game of predator and prey would recalibrate to a new rhythm, one dictated by clouds and seasons, not the moon. In the ocean, entire ecosystems are synchronized by the moon. On the Great Barrier Reef, over 100 species of coral time their annual mass spawning to just a few nights after the November full moon. This creates an underwater blizzard that maximizes fertilization. Without that lunar cue, the incredible synchrony would fracture. Spawning would become patchy and mistimed, a mere drizzle instead of a storm, with far lower reproductive success. On the beaches of California, the famous grunion runs are timed to the highest spring tides following full and new moons. These small fish ride the waves ashore to lay their eggs in the sand. With only the sun's tide, the highest highs are lower and the signal is weaker. A few fish would still show up, but the spectacular shoulder-to-shoulder midnight runs would likely thin out to a shadow of their former glory. When sea turtle hatchlings emerge from their nests, they instinctively crawl toward the brightest, lowest horizon, which, on a natural beach, is the ocean. The glow of moonlight on the surf often makes this the most obvious target. Remove the moon, and that natural contrast can drop by over 100 times. Now, the faint artificial light from a distant house or street lamp could easily become the brightest thing they see, luring them in the wrong direction. Here's a final twist. While smaller tides might sound like a good thing, less coastal flooding, they can actually make some coastal waters dirtier. That powerful tidal flushing we talked about keeps bays clean. With weaker tides, pollutants and excess nutrients hang around longer, leading to murkier water and more frequent algae blooms. You might dodge the highest storm tides, but you could trade them for chronically unhealthy water. Humanity's expansion into space would also be dramatically affected. Many advanced mission plans rely on using stable parking spots in space, called Lagrange points, which are created by the gravitational balance between the Earth and Moon. NASA's planned Lunar Gateway Station, for example, is designed for an orbit around the Earth-Moon L2 point. Without the Moon, these cislunar balance points and the fuel-saving highways between them vanish instantly. Any spacecraft using one would immediately drift off course. Satellites in orbit purely around the Earth would be fine. In fact, for geostationary satellites, life gets a little easier. The Moon's gravity causes a slow perturbation that has to be corrected for. With the Moon gone, station keeping would require slightly less fuel. But the big loss is strategic. The Moon is a crucial stepping stone, a gravity assist partner, and a navigational landmark for deep space exploration. Those playbooks would need a total rewrite. So let's zoom out. Vanishing the Moon doesn't just make our nights darker. It immediately quiets the oceans, silences tidal power plants, and ends eclipses forever. Over human lifetimes, it forces countless ecosystems to find a new rhythm. And over the deep time of geology, it retunes the very clockwork of our planet, slowing its wobble and unchaining its tilt. In some distant future, Antarctica could get summers as hot as the tropics. The Moon was never just a nightlight. It's the governor on the entire machine. If you like clear walkthroughs of how the hidden gears of our world really work, you are in the right place. Subscribe and drop a like if this sparked a thought. There are deep dives on tides, seasons, planes, power grids, and more right here on the channel. Keep your eyes on the night sky. With or without a moon, there's always something amazing up there. See you next time.